fact, something further than Lagrange interpolation called Hermite interpolation. All of these are consequences of this Chinese remainder theorem. So this is a general one. So let us see how to prove it. So proof of Chinese remainder theorem. So there are three parts. I'll do the proof one by one. And the first part is actually the easiest. The easiest part says that the kernel of phi is the intersection of all these ideals. So where does phi go from? Phi goes from R to R mod I1 cross R mod I2 cross R mod I2. And what is phi? Phi of x is just x bar, x bar, x bar everywhere. So we want to calculate the kernel of phi. So kernel of phi, this is now a ring. These are ring maps. So the kernel is everything that goes to 0. So occur phi is the set of all x in R such that phi of x is 0. 0 where? 0 in this ring. In that ring means the 0 of that ring is just 0 bar, 0 bar, 0 bar. That's the 0. And what does this mean? That means the set of all x in R such that phi of x, as I said, is just x bar, should be equal to 0 bar, 0 bar, 0. Now, what does this mean? This doesn't mean that x must be 0, right? This definitely does not mean that x must be 0. If x bar and 0 bar are equal, it doesn't mean x and 0 are equal. It just means that x minus 0 belongs to that ideal, whichever ideal you're considering. This implies, so now note that x bar equals this when, if and only if, the first x bar should be 0 bar, the second x bar should be 0 bar, the third x bar should be 0 bar, the last x bar should be 0 bar. Now it might seem funny to write it this way. Why am I writing the same equation so many times? The reason I'm doing this is because all these x bars mean different things. The first x bar means x plus I1. The second x bar means x plus I2. The third x bar is x plus I3, so on. These are not the same equation, but different equation. They say different things. So when is x bar equal to 0 bar? This means that x minus 0 belongs to I1. This says x minus 0 belongs to I2. The third one says x minus 0 belongs to I3. And so on up to the last one says x minus 0 belongs to Ik. This is an if and only if condition for x bar to be 0 bar in I1, in R mod I1, in R mod I2, up to R mod Ik. And so, of course, this just means that x belongs to the intersection of I1, I2, I3, up through Ik. So that's it. That finishes the proof of the first part. The kernel of this ring homomorphism phi is the intersection of all the ideals x1 up to xk. Now let's look at the second part. The second part says, suppose that these ideals are co-maximal pairwise. That means any two of them add up to the whole ring. Then we want to show that the intersection and the product are the same. So for this, let me first recall. So we are going to do part 2 by induction. By induction on K. Okay, so there's a basis case. The basis case is when K is 2, when there are two ideals. So basis case is when K equals 2. So I1 and I2 are co-maximal, and we want to show that I1 intersect I2 equals I1 I2. We have already done this actually. So how did we do this? So recall that in general, for any two ideals, I plus j times I intersect j is contained in ij, is contained in I intersect j, always for any two ideals. And so if they are co-maximal, so if I plus j is R, the whole ring, then what does this equation say? This becomes R. So what is R times any ideal? R times any ideal is just that ideal itself. So it just says I intersect j is contained in ij is contained in I intersect j. That means all of them must be equal, which means I intersect j equals ij. That's what we're trying to show. I1 intersect I2 equals I1 I2 if I1 and I2 are co-maximal. So here I called it I and j, but whatever, you could call it I1. So we have done the basis case. So now proceed. Now assume that whenever we have less than k ideals that are pairwise co-maximal, then their product and intersection are the same. This is the inductive assumption. So in particular, this implies hence I2 intersect I3 intersect IK. That's less than k of them. That's k minus 1 ideals. And they are also pairwise co-maximal. The original set was pairwise co-maximal. Of course, these are also pairwise co-maximal. So their intersection is just equal to the product I2, I3 up to IK. Now, what do we want? We want to take I1 intersect I2 intersect I3 up to IK. Consider I1 intersect I2 intersect IK. By what I just said, it's I1 intersect I2, I3, the product. This I want to show is the product of I1, I2, I3 up to IK. This is what I want to show. Now I would be able to do it if you knew that this ideal and this ideal are co-maximal. If you knew that I1 and the product of I2 up to IK are co-maximal, then we have already did the k equal to 2 case. So by the k equal to 2 case, we will have proved it. So what remains to be seen is, so to finish the proof, we need to see that I1 and the product of I2 up to IK are co-maximal. That we don't know yet. We are not given that. We are given that I1 and I2 are co-maximal, I1 and I3 are co-maximal, so on and so forth. But we don't know about I1 and the product of all of them. So we need to prove this. So this is what we need to prove. So we prove this. So we prove this as follows. So what do we know? I1 and I2 are co-maximal, right? That means I1 plus I2 is equal to R. That means 1 belongs to I1 plus I2. Then to say that a pair of ideals are co-maximal is the same as saying that there is an element in one of them and an element in the other of them that adds up to 1. That's all it means to say co-maximal. So I1 and I2 are co-maximal. So we can find an A2. I'll write A2 plus B2 equals 1, where A2 is in I1, B2 is in I2. I'm using rather peculiar choice of notation. You'll see why. Right? Why is this equation hold? We know that there exists A1 and A2 and B2 such that this equation holds. That's because I1 and I2 are co-maximal. So some element of I1 plus some element of I2 must be equal to 1 because it generates the unit ideal. Similarly, A3 plus B3 is equal to 1, where A3 is in I1 and B3 is in I3. This is because I1 and I3 are co-maximal. So we get a whole set of elements. AK plus BK is 1, where AK is in I1 and BK is in IK. These elements exist because as I said already, I1, I2 are co-maximal. I1, I3 are co-maximal, etc., etc. I1, Ik are co-maximal. Now I want to use these elements to get an element in the product of I2 up to Ik and an element in I1 which add up to 1. So I want one element which is in the product of I2 up to Ik and one element in I1 which add up to 1. So the natural thing to do is this element is in I2, this element is in I3, this element is in Ik. So B2 is in I2, B3 is in I3, Bk is in Ik. We can just try to take the product of B2, B3, so on and so forth up to Bk. That element certainly belongs to the product of the ideals I2, I3 up to Ik. So observe that. The product B2, B3, B4, so on up to Bk. This belongs to the product ideal I2, I3, I4 up to Ik. In fact, the product ideal is generated by all such elements. That's how we define the product. So this product belongs to I2, I3, I4 up to Ik. But we can also write this in a different way. So, but this is also equals B2 is 1 minus A2, B3 is 1 minus A3, so on and so forth up to Bk is 1 minus A2. So this element B1, B2, B3 up to Bk is also equal to 1 minus A2 into 1 minus A3, so on and so forth up to 1 minus Ak. Now this you can expand. You can write this as 1 minus A2 minus A3 minus up to Ak plus A2, A3 plus A2, A4 up to Ak minus 1 Ak minus 3 at a time. A2, A3, A4 up to Ak minus 2, Ak minus 1 Ak and so on and so forth. We'll get one long expression. We'll get 2 power k minus 1 terms. 2 to the power k minus 1 terms. Why so many terms? So here are 2 terms, here are 2 terms, here are 2 terms. So 2 times 2 times 2, 2 power k minus 1 terms. And if you write down all those 2 power k minus 1 terms, what do you observe? What you observe is A2 is in I1, A3 is in I1, Ak is in I1. So all these terms are in I1. This is also in I1, 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 this is also in I1. Every term is in I1 except the first term, which is 1. Right? The element 1 is not in I1, but since A2 to Ak are in I1, all the rest of the terms are in I1. So you can write this as 1 plus A, where A belongs to I1. And I claim that we are mostly done. So what have we seen? So we have seen that, so B1 up to Bk equals 1 plus A, which belongs to, not which belongs to, B1 up to Bk is 1 plus A. So 1 can be written as minus A plus B2, B3 up to Bk. This is an element in I1. And this is an element in I2 intersect I2, I3 up to Ik. So we have seen that the element 1 can be written as a sum of elements in the ideal I1 and in the ideal I2, I3 up to Ik. Okay, so that means this and this are co-maximal. Hence, I1 and this product ideal are co-maximal. And so their sum and intersection are the same. Their intersection and product are the same. So I1 intersect I2 up to Ik is equal to I1 I2 up to Ik. So what does this do for us? Just go back a little bit. So here we have I1 intersect I2, I3 up to Ik, and I just showed that this is equal to I1, I2 up to Ik. And therefore, the intersection of I1 up to Ik is equal to the product of I1 up to Ik. So this finishes the proof of the second step. So now let's get to the proof of the third step. The third step, if you see, is an if and only if statement. So in the three parts, the third step is an if and only if statement. It says phi is surjective if and only if the ideals are pairwise co-maximal. So I want to do two things. I want to show that if it is surjective, then the ideals are pairwise co-maximal. And if the ideals are pairwise co-maximal, then phi is surjective. So I'll have to show two directions. So let me do both of those directions. So first, this direction, that is, suppose that phi is surjective. So want to show that I1 up to Ik are pairwise co-maximal. Okay. So to do this, it's very not hard to do this. So remember that phi goes from R to R mod I1 cross R mod I2 cross R mod Ik. So I know that phi is surjective. That means no matter what element I take in these products, there will be some element of R under phi which will go to that element. So consider the element 0 bar, 0 bar, everywhere 0 bar except a single 1 bar. This is in the ith position. R mod I sub I. All the others are 0 except in R mod I take 1 bar. So this is an element which belongs on this side. So this is some element which belongs to the product of the rings R mod I1 cross R mod I2 up to R mod Ik. But phi is surjective, we are assuming, which means there must be some element in R such that phi of x equals this. Since phi is surjective, there exists x in R such that phi of x equals this element. But we also know that phi of x is x bar, x bar, x bar. So x bar, x bar, x bar equals 0 bar, 0 bar, except a single 1 bar. This one. So what does this equation mean? This equation means that, so this is the ith position. And let us say somewhere here is the jth position. Let's say that's the jth position. So just look at the ith position, the jth position. So x bar in the ith position equals 1 bar. So x bar equals 1 bar in R mod I sub I. And in the jth position, x bar equals 0 bar in R mod I sub j. Let us just try and understand. These equations are represented in terms of bars. That means in terms of cosets. If you don't want to say it in terms of cosets, what does it say? This just says that x minus 1 belongs to I sub I. And this just says that x belongs to I sub j. These mean the same thing. To say that x minus 1 is in I sub I is the same as saying x bar equals 1 bar in R mod I sub I. So I found an element x which satisfies these two conditions. X minus 1 is in II and x belongs to I sub j. And hence 1 equals x minus x minus 1. This belongs to I sub j plus I sub I. This part is an I sub I, that part is an I sub j. So I've written 1 as a sum of elements of I sub I and I sub j, which means these two are homomaximal. Okay, so we have seen that if phi is surjective, then the ideals are pairwise homomaximal. Now, what about the other? What about the other side? The other side is, so to prove this side, we need to assume that I sub j's are homomaximal, pairwise homomaximal. And show that phi is surjective. So I want to make one observation about this. This observation will be a little familiar because we have already done Lagrange interpolation and already done the classical Chinese remainder theorem. So this observation should be somewhat familiar to you. And this observation is the following. So I claim that it is enough to show that the element 1 bar and everywhere else 0 bar is in the image of phi. So let's make sure that we understand why we are saying this. To say that phi is surjective, we want to show that every element is in the image of phi. I am saying, no, you don't have to worry about every element. You only have to worry about this element 1 bar, 0 bar, 0 bar, 0 bar. If you know that that is there, then every element will also be there. So why is that? Because if this is an image phi, so is similarly 0 bar, 1 bar, 0 bar. This also will be in the image of phi. And all the rest also. And all the others of this form. Once you know this, now take a random, now take an arbitrary let's say B1 bar, B2 bar, up to Bk. I want to show that this is phi of something. So I want to show this is phi of x for some x in R. But we will write this element like this. So we can write this element as let me say B1 times 1 bar, 0 bar, 0 bar, 0 bar plus B2 times 0 bar, 1 bar, 0 bar up to Bk times 0 bar, 0 bar, last one being 1 bar. So what exactly does this mean? Where is all of this happening? What does it mean to write this element in this form? So if I want to explain what writing this element in this form means, I'll have to say something about R modules. So since I haven't yet discussed R modules, maybe I'll not say it exactly this way. So let me just say it slightly differently. So slightly differently, I'll say the following. So we know that there exists an x1 in R such that phi of x1 equals 1 bar, 0 bar, 0 bar, 0. And similarly, x2, x3 up to xk. Okay. So what will be phi of x2? Phi of x2, for example, will be 0 bar, 1 bar, 0 bar. How do we know? I mean, we don't know it yet. I'm saying, suppose we know this. Suppose we know that all of these elements of this kind are in the image, then we know that there will be exist some x1, some x2 such that these equations are satisfied. Now just take x to be b1 x1 plus b2 x2 up to bk xk. Right? And let us try to calculate what is phi of x. Phi of x, because phi is a homomorphism, so this will be phi of b1 x1 plus phi of b2 x2 up to phi of bk xk. Now what is phi of b1 x1? Phi of b1 is b1 bar up to b1 bar, all b1 bars. Phi of x1 we know as 1 bar, 0 bar, 0 bar. It's also equal to x1 bar, but we chose x1 such that phi of x1 is 1 bar, 0 bar, 0 bar, 0 bar plus b2 bar, b2 bar, b2 bar times 0 bar, 1 bar, and so on and so forth up to bk bar, bk bar, bk bar times 0 bar, 0 bar, all zeros except the last one, which is 1. And we know how to add and multiply in this ring. If you add, you see multiplication is component wise, addition is component wise. So if you multiply and add and do all the calculations, you will just get b1 bar, b2 bar up to bk bar. So therefore, we have found an x such that phi of x is b1 bar, b2 bar up to bk bar. So this is how we did. This is how we did the Chinese remainder theorem classically also. This is how we did Lagrange interpolation also. The same idea applies to much more generally in a commutative ring with identity to prove this Chinese remainder theorem. So what remains to be done? So remains to show there exists x1 such that phi of x1, which is x1 bar, x1 bar, x1 bar equals 0 bar, 0, 1 bar, 0 bar, 0 bar. But this is what we did in the previous step actually, right? If you go back to previous step. And check. This was what was done. Even in that step, this is the main idea. We want to find an element which is 1 mod I1 and it is 0 mod I2, I3 and all. So that means it belongs to the intersection or it belongs to the product of I2, I3 up to Ik. We did that. We found an element such that it minus 1 belonged to all of 1 plus A was B2 up to Bk. So we showed there exists B2 up to Bk in I2, I3 up to Ik such that B2 up to Bk equals 1 plus A. So that means we can take our x, we can take our x1 to be B2 up to Bk. And therefore, we are finished with the proof of the Chinese remainder theorem. So this is, if you're looking at this for the very first time, it is a little bit abstract, and this is being done in a very general ring with very few hypotheses. Nothing is assumed really. So this is a very general kind of proof. So it might be a little bit uncomfortable initially, but after seeing examples, the same way of proof for the classical case and for the Lagrange interpolation, I hope that this was not too bad. Okay, so we have finished the proof of the Chinese remainder. What do we do with this? So what I want to do with this is, first I want to show that this Chinese remainder theorem implies the classical Chinese remainder theorem. Okay, but maybe 1 second before I go to that. So let me observe the following. So we have the following corollary, and this is a very important corollary. The important corollary says in a ring R, if the ideals I1 up to Ik are pairwise co-maximal, then the ring R mod, the intersection, and remember the intersection is the same as the product, is isomorphic to R mod I1 cross R mod I2 cross R mod Ik. And what is the proof of this corollary? We have already done most of it. So why is that proof? So we know that phi is a ring homomorphism from R to R mod I1 up to R mod Ik is surjective. It is surjective because that's what the Chinese remainder theorem said. The Chinese remainder theorem said that if they are pairwise co-maximal, then phi is surjective. And we also know that curve phi is the ideal I1 intersect I2 intersect Ik, which is also the product of I1 and I2. So we have a surjective ring homomorphism, and the kernel is some ideal. Then R mod, that ideal, is isomorphic to the ring on the other side. That's the first isomorphism. So by the first isomorphism theorem, R mod, the kernel, is isomorphic to the image, but it's surjective, so the image is everything. Why is this helpful? So we have finished the proof, right? We have finished the proof of the corollary. So why is this helpful? So it's helpful for the following reason. So lots of times it helps you decompose rings that you want into rings that are possibly simpler. So for example, so suppose I take Zmod, say 12. So this is the ring. This ring is the ring R is equal to Z mod 12Z. Now let's look at the ideal 12Z. The ideal 12Z, I claim, is the intersection of 4Z and 3Z. The ideal 12Z is the intersection of the two ideals 4Z and 3Z. 12Z means all multiples of 12. 4Z is all multiples of 4. If a number is a multiple of 4 and a multiple of 3, it's a multiple of 12, if and only, right? So 12Z is the intersection of these two. So Z mod 12Z is Z mod 4Z intersect 3Z. And note that the ideals 4Z and 3Z are co-maximal. So 4Z plus 3Z is the whole of Z. Why is that? Because I can take 4 here and minus 3 here, and I'll get 1. Once I get 1, that means they are co-maximal. If I can get 1, adding an element of two ideals, if I get 1, then those two ideals are co-maximal. So this is co-maximal. So by the Chinese remainder theorem, so this is isomorphic to Z mod 4Z cross Z mod 3Z. Now I should mention that isomorphic. What are they isomorphic? Are they abelian groups isomorphic or ring isomorphic, or what isomorphic are they? So this Chinese remainder theorem is a little bit powerful because it's a ring isomorphism as rings. It implies that they are isomorphic as abelian groups, but it is stronger. So I'm saying that the rings Z mod 12Z and the Z mod 4Z cross Z mod 3Z are isomorphic rings, right? And the isomorphism, if you want to actually do it, is given by that phi. You have to follow through that proof and see that that phi is actually an isomorphism between Z mod 12Z and Z mod 4Z cross Z mod 3Z. So things of this kind. So another example for this, for instance, if you take the ring, say QX mod x squared minus x. So this is the ring, right? So Qx is a ring. The ideal generated by x squared minus x is some ideal in that ring. I want to see what is the ring Qx mod x squared minus x. So this is the same as Qx mod the ideal generated by x into x minus 1. And here the ideals x and x minus 1 are clearly co-maximal. So I hope it's clear to everybody that these two ideals are co-maximal, obviously, because x plus minus 1 times x minus 1 equals 1. Obviously, I can get 1. If I give you x and x minus 1, certainly you can get 1 by combining them. So that means these two ideals are co-maximal. And hence, so Qx mod x squared minus x is isomorphic to Qx mod the ideal generated by x cross Qx mod the ideal generated by x minus 1. This certainly is a consequence of the Chinese remainder theorem. But using this consequence of the Chinese remainder theorem, we can go a little further. So what further can you go? So we can ask, what about this Qx mod x separately? What ring is this and what ring is this?
Q.
I claim that both those rings are isomorphic to Q. I claim that Qx mod x is isomorphic to Q as a ring, and Qx mod x minus 1 is also isomorphic to Q as a ring. And each of that can be proved again using the first isomorphism theorem. So claim, I'll do it for this one. The other one is easier, or the same actually. So Qx mod the ideal generated by x minus 1 is isomorphic to Q. In general, how do you show that some quotient is isomorphic to something? Always, almost always, the method is you will get a surjective homomorphism from Qx onto Q and show that the kernel is x minus 1. So we get a surjective homomorphism from Qx to Q, whose kernel is the ideal generated by x minus 1. If you do that, then by the first isomorphism theorem, Qx mod x minus 1 will be isomorphic to Q as rings. Then done by first isomorphism. So how do we get a surjective homomorphism from Qx to Q? So I have Qx, I have Q, and I want this homomorphism. So I want to take every element of Qx to some element of Q. I want to take elements of Qx to elements of Q. I want a surjective homomorphism. So there are many such natural homomorphisms. For example, you could set x equal to 0. If you set x equal to 0 in a polynomial, take a polynomial and just take its constant term. If you just take the constant term of the polynomial, that actually gives you a homomorphism from Qx to Q. You can check that the constant term of a sum is the sum of the constant terms. Constant term of a product is the product of the constant terms. So actually this gives you a ring homomorphism from Qx to Q. But you need not set x equal to 0. You can set x equal to anything you want. And you must choose that thing carefully. What you would like is that x minus 1 should be in the kernel. So you want a homomorphism such that, we'll call it phi, such that x minus 1 belongs to the kernel of phi. In fact, we want x minus 1, the ideal generated by x minus 1, to be exactly equal to the kernel of phi. But for now, first let us try to find one where x minus 1 is in the kernel of phi. So such a homomorphism is easy to define. So we can define phi of any polynomial to be f of 1. So I'll just define phi of f of x to be f of 1. So evaluate that polynomial of 1. So this is clearly a homomorphism. So this is homomorphism from Qx to Q. And further, this homomorphism is also surjective. Also, this is surjective. That's easy, right? So it's a surjective homomorphism from Qx to Q. Now I claim that x minus 1 is in the kernel of phi. Okay? X minus 1 belongs to the kernel of phi. I.e., phi of x minus 1 is 0. That's what it means to belong to the kernel of phi. But what is phi of x minus 1? Phi of f of x is f evaluated at 1. So phi of x minus 1 is x minus 1 evaluated at x equal to 1. And that's of course 1 minus 1, that's 0. So x minus 1 is in the kernel of phi. But I want to say it's not just in the kernel of phi. I want to say it is exactly equal to the kernel of phi. That is, the ideal generated by x minus 1 is exactly equal to curve phi. Further, curve phi is the ideal generated by x minus 1. That means anything in the kernel I want to show is divisible by x minus 1. That is what it means. So to show this, so suppose some f of x belongs to the kernel of phi. What does it mean? That means f of 1 is 0 because phi of f of x is actually equal to f of 1. That's how we define phi. So if f of x is in kernel of phi, it's the same as saying f of 1 is 0. I want to show that x minus 1 divides f of x. So by the Euclidean algorithm, or if you just say remainder theorem, you're done. But let me just say it a little more detailed. By the Euclidean algorithm, f of x equals x minus 1 qx plus a remainder. That remainder is actually a polynomial in x, but it's of degree less than 1. So that means it's of degree 0. That means it's just some constant. So f of x equals x minus 1 qx for some polynomial qx and some remainder just in q. But f of 1 is 0. This means 1 minus 1 qx. If I set 1, it becomes 0. So that means 0 times something plus r is 0. This means r is 0. And this means f of x equals x minus 1 qx. And so f of x belongs to the ideal generated by x minus 1. So we have proved that the kernel of phi is actually equal to the ideal generated by x minus 1. And once we know that, as I said by the first isomorphism theorem, qx mod curve phi is isomorphic to q. That means qx mod x minus 1 is isomorphic to q. Qx mod x minus 1 is isomorphic to q. And similarly, one shows that qx mod x is isomorphic to q. And so finally, the conclusion of all of this is what might seem to be rather surprising at first. Hence, if you take the ring qx mod the ideal generated by x squared minus x, this is isomorphic to q cross q. These two rings look very different at first sight, right? If you look at these two rings, they don't look like anything similar, right? Qx mod x squared minus x is some quotient of some polynomial ring in one variable over q. Q cross q, on the other hand, just consists of all the AB, such that A and B belong to Q with component-wise multiplication and addition. What does this thing with component-wise addition and multiplication have to do with this, which is something involving polynomials? But actually, they are isomorphic rings. So this is the kind of the power of the Chinese remainder theorem in general, right? You can show that various rings. This is clearly a very simple ring. Q cross Q is a ring which we can understand very well. This, on the other hand, you might think is slightly more complicated, but actually it is not. It's just the same as Q cross Q. Up to isomorphism, it is the same ring. Okay, so let's see, where was I? So I was trying to give you some examples of this Chinese remainder theorem. In particular, this corollary. This corollary is this important one. Lots of books. This is what will be called the Chinese remainder theorem, right? That Rmod, the intersection of ideals, is isomorphic to Rmod, the individual ideals, the product, when the ideals are co-maximal. That is the Chinese remainder theorem. Okay, fine. So now let's get to trying to see how does this imply the classical Chinese remainder theorem. So how does general CRT imply the classical CRT? The classical CRT said what? That if I had, if M and N are co-prime, then X is congruent to A mod M and X is congruent to B mod N as a solution. That was the classical. So if you apply the general Chinese remainder theorem to Z, so consider the ring Z, the ideals MZ and NZ are co-maximal if M and N are co-prime. So let's make sure we understand this. This is an important statement. The statement that the ideals MZ and NZ are co-maximal, if not, it's not if, it's actually if and only if, right? The ideals MZ and NZ are co-maximal if and only if M and N are co-prime. So why is this? If M and N are co-prime, that means that GCD is 1. And we know that by the generalized Euclidean algorithm, you can write 1 as a combination of M and N as AM plus BN. AM belongs to the ideal MZ, BN belongs to the ideal NZ. So that means 1 can be written as something in MZ plus something in NZ. That means they are co-maximal. Conversely, if they are co-maximal, then AM plus BN must be equal to 1. And that means they cannot have a GCD. If M and N have a GCD, that GCD would have to divide 1 also. That means the GCD of M and N is 1. So to say that MZ and NZ are co-maximal is the same as saying M and N are co-prime. So by this Chinese remainder theorem, we get Z mod MZ intersect NZ is isomorphic to Z mod MZ cross Z mod NZ. And what is this isomorphism? It's given by phi, remember, right? The phi was that homomorphism of where we got this isomorphism from. Now, what does this mean? Okay, or we could say, or let's just say, phi is surjective. So Z to Z mod MZ cross Z mod NZ is surjective. That is also part of the Chinese remainder, right? That's the main part, in fact. Right? So this is surjective. So if you are given A bar and B bar, so given A and B in Z, A bar and B bar belong to Z mod MZ and Z mod NZ. And since this phi is surjective, there exists X in Z such that phi of X equals A bar B bar. This means what? That means X bar equals A bar B bar, which means X minus A belongs to MZ and Y minus B, X minus B belongs to NZ. That's just the same as saying X is congruent to A mod M and X is congruent to B mod M. So we have solved. Okay. So this general Chinese remainder theorem implies the classical Chinese remainder theorem. Also, so this is one thing. Then the other thing is the similarly. Oh, okay, it's not quite similarly. Okay, let me do it. So similarly, the general CRT implies Lagrange interpolation. For this, we need to do a little bit more work. So how does the general CRT imply Lagrange interpolation? So what do we do in Lagrange interpolation? So we are given points x1, y1, x2, y2 up to xk, yk, and we want a polynomial whose graph passes through all these points. A polynomial of degree at most k minus 1, whose graph passes through all these points. That's what we want. What does this have to do with the Chinese-Remainder theorem? So where are the co-maximal ideals? What is happening? Which ring? All these questions, right? So the ring is clear. So consider the ring Kx, where K is that field. So which field is that? The field K is where all these points x1, y1, x2, y2, xk, yk lie. All these xi's and yi's are elements of some field, and I want to consider that field, right? So consider Kx and look at the ideals. X minus x1, x minus x2, up to x minus xk. The ideal generated by x minus x1, the ideal generated by x minus x2, the ideal generated by x minus xk. So these are k different ideals, I1, I2, up to ik. So these are all ideals in kx. What about these ideals? I claim that these ideals are co-maximal, pairwise. These ideals are pairwise co-maximal. That's very easy to see. What does it mean to say co-maximal? That just means that I plus j, if I take an I sub I and an I sub j, they add up to R. So we want to show that I sub I plus I sub j is the whole ring. Whole ring is kx. Whenever I is not equal to j. If I take two of them, I want to say that these two ideals add up to the whole ring. But what is I sub I plus I sub j? I sub I is x minus xi, and I sub j is x minus xj. What is the ideal generated by x minus xi plus the ideal generated by x minus xj? In general, if you have generators for one ideal and generators for the other ideal, the sum will be generated by all those generators put together. So this is just the ideal generated by x minus xi and x minus xj in the ring Kx, of course. But notice that if you have x minus xi and x minus xj, note that if I subtract x minus xj minus x minus xi, we'll call this ideal temporarily, let's call this just I. Okay? So belongs to I. But what does this mean? This means xi minus xj belongs to I. This element is an element in K, and this element is not zero because I took all the little xi's to be distinct. So I have a non-zero element of that field in K, in I, which means multiplying by 1 by xi minus xj, we get 1 belongs to I. That means I must be the whole ring. To say that the ideal is the whole ring is the same as saying that 1 belongs to that ideal. So we see that the sum of these two ideals is the whole ring. So these ideals are pairwise co-maximal. Once we know these ideals are pairwise co-maximal, we can apply the Chinese-Remainder theorem. Hence, by the general CRT, what does it say? It says Kx mod the ideal generated by their intersection, which is also the product, which is x minus x1 times x minus x2 up to x minus xk. This is the ideal, which is the product, which is also the intersection because they are pairwise co-maximal, is isomorphic to kx mod x minus x1 cross kx mod x minus x2 cross kx mod x minus xk. So this is what the Chinese-Remainder theorem says. How are we going to use it to do interpolate?
வெளிய வந்தாடி
மீட்டிங்
ஓடிக்கிட்டு இருக்காங்க
yeah, so we will interpolate as follows. So what we will do is, so hence consider the element little y1 bar, little y2 bar, up to little yk bar in this. This is some element, right? I can take the coset of any element of kx. I am just taking the coset of the constant element y1 bar, y2 bar, yk bar. I can take any elements I want. I can take polynomial cosets, but I don't want for this one. I'm just taking the constant polynomial y1, its coset in kx mod x minus x1. Then I take the constant polynomial y2, its coset in kx mod x minus x2, so on and so forth. So I take this one. So there exists some fx in kx such that fx bar equals y1 bar, y2 bar up to yk bar. That's what the Chineseeliminator theorem says, right? In fact, because we are saying this is an isomorphism, this fx is actually unique up to the, okay, I'll come to uniqueness later. Let me say that later. First of all, there exists an fx in kx such that this happens. What does this mean? This means fx minus y1 belongs to the ideal x minus x1. Fx minus y2 belongs to x minus x2. So fx minus yk belongs to x minus x. That means what? So fx minus y1 equals x minus x1 some gx or g1x. Fx minus y2 is x minus x2 g2x, so on and so forth. Okay, now just set in the first equation, suppose I set x equal to x1, f of x1 minus y1 equals 0. Setting x equals x1 in the first equation. Similarly, f of x2 minus y2 is 0. So on and so forth up to f of xk minus yk is 0. And therefore, our polynomial fx, hence fx, the graph of fx goes through all the points x1, y1 up through xk, yk. But remember, we said something about the degree. So we said we want to find a polynomial of degree at most k minus 1, which will work. So far, this general Chineseeliminator theorem, there's nothing about degrees. In fact, it's not even in a polynomial ring. So we can't say anything about degrees so far, unless we look carefully at what it says. So it's this ring, which is isomorphic to that side. So in fact, I can take, so this fx, so let's take fx. So we want to say something about the degree of fx. So let me just observe that fx bar belongs to kx mod x minus x1 into x minus x2 up to x minus x3. So this thing is a degree k polynomial in capital X. So I have a degree k polynomial. I want to say that any element of that ring can be represented as a coset which is represented by a degree k minus 1 polynomial. So my claim, any element of kx mod this can be written as fx bar for fx having degree less than or equal to k minus 1. I want to say that it can be written as fx bar for fx having degree less than or equal to k minus 1 and in fact unique. There is a unique fx. If I take any element of this quotient ring, there is a unique fx of degree less than or equal to k minus 1 such that that element is the same as fx bar. And this is easy to see. So proof of this claim is again Euclidean algorithm. So what is a general element of that ring? What is the general element of this? Let's call this ring R. What is the general element of R? So a general element of R is a coset. It is a coset with respect to this idea. Right? The general element of R, it is of the form some px plus the ideal generated by this product. But you see, this is of degree k. It's a monic polynomial of degree k. Doesn't matter that it's monic. It's some polynomial of degree k. So you can divide px by this and write it as qx times this polynomial plus a remainder, where the remainder has degree less than k. So write px as qx times this polynomial plus rx, where the degree of Rx is at most k minus 1, strictly smaller than k. That's what the Euclidean algorithm for polynomial rings over a field says. So I can always write my px in this form. And then observe that px plus, if I call this ideal I, px plus I is qx into x minus x1 up to x minus xk plus rx plus I. But notice that this whole term belongs to I, because x minus x1 into x minus x2 into x minus xk belongs to I. That whole term belongs to I. So this is equal to just rx plus I. And now rx has degree less than or equal to k minus 1. So any element which is a px plus I can always be represented by a polynomial of degree less than or equal to k minus 1. What this means is, so we could have chosen the previous fx to be of degree less than or equal to k minus 1. And so there exists a polynomial of degree less than or equal to k minus 1, which satisfies all those equations, which is the classical Lagrange interpolation. So we see how this Chinese remainder theorem implies also the Lagrange interpolation theorem. But in fact, it does more than that. More than Lagrange interpolation, it implies something called Hermite interpolation. So that's the next thing I'll do. Hermite interpolation. So rather than do it in general, which will involve lots of symbols, I will do one example, and I hope you will get the idea from that example. So what is a typical problem? So the problem is like this. So find a polynomial of degree less than or equal to, I'll tell you what the degree is, such that f of 1 is 2, f dash 1 is 3, f double dash 1 is 4, f of 2 is 5, f dash 2 is 6. This is the problem, right? And what degree? Notice that I have given you 1, 2, 3, 4, 5 conditions, right? Since I have given you 5 conditions, probably the polynomial should be of degree 4. A degree 4 polynomial will have 5 coefficients, right? The constant term, the coefficient of x square, x cube, x and x4, right? So I want a polynomial of degree less than or equal to 4, such that satisfying the condition that f of 1 is 2, f dash 1 is 3, f double dash 1 is 4, f of 2 is 5, and f dash 2 is 6. Sorry, it's not clear. how do we solve this problem? This is called the Hermite interpolation. Okay. So to actually solve it will involve some effort. I'll just tell you how to get the solution, right? I'll leave the calculations, but I'll tell you how we get the solution. So first of all, so observe that if I take the polynomial 2 plus 3x minus 1, 3 by 1 factorial, plus 4 by 2 factorial x minus 1 squared. Let's take this polynomial. So this is like the Taylor expansion, right? In the Taylor expansion, the coefficients will be some an by n factorials will come. So let's take this polynomial and let's see what properties this polynomial has. So let's call this, say, let's call this P of x. Suppose this is P of x. So what is P of 1? P of 1 is 2, right? And what is P dash 1? To get P dash 1, you have to take the derivative. So when you take the derivative, this term will go away. And when you take the derivative of this with respect, you just get 3, right? And this term will give something times x minus 1. So when you substitute 1, that term also will go away. So P dash 1 is 3. And if you calculate P double dash 1, this term will go away and this term, both these terms go away. So what is left is only this term, and there'll be a 2 factorial which will be cancelled by this 2 which comes down, and then another 1 which comes down. So finally you'll be left with 4. So this polynomial Px satisfies all of these conditions. Okay, so it's easy to find a polynomial Px which satisfies all the derivative conditions at a single point. Similarly, if you take Qx equals 5 plus 6 into x minus 2. So what does this satisfy? This satisfies Q of 2 is 5. And if you do Q dash 2, it will be 6. So Q of x satisfies all these conditions. So Px satisfies these conditions. Now Qx satisfies those conditions. But we want a single polynomial of degree at most 4 which satisfies each of these conditions. So how do we do that? So how to find f of x? So as I said, I won't do the calculation, but I'll just tell you how to do it. So the key observation is the following. So the ideals if I take x minus 2 cube, x minus 1 cube, the ideal generated by x minus 1 cube and the ideal generated by x minus 2 square are co-maximum. This is my claim. This is an observation I want to make. That means if I take the ideal generated by these two, I get the whole of kx, i.e. the ideal generated by x minus 1 cube and x minus 2 squared is the whole of kx. And why is this? Because we know that k of x is a principal ideal domain. So every ideal there is principal. So this ideal must be a principal ideal. If it's a principal ideal and it's generated by some h of x, then that h of x must certainly divide x minus 1 cube and it must divide x minus 2 squared. But the only thing that divides these two are co-prime. So the only thing that divides these two is a constant polynomial. So that means that the ideal that they generate is the whole of kx. So these two are co-maximum. And hence, kx to kx mod x minus 1 cube cross kx mod x minus 2 squared is surjective. That's what the general Chinese remainder theorem says. So there exists an fx in kx. I don't know what the degree is yet, such that fx bar equals px bar qx bar. I can take anything I want. It's surjective, so I can take any element I want in this ring will be the image of some fx. So what does this mean? I.e. fx minus px is divisible by x minus 1 cube, and fx minus qx is divisible by x minus 2 squared. So what does this mean? So now, so here is an exercise for you. Show that this fx satisfies all conditions given, all the 5 conditions, and so solves our problem. But this fx, we want it to be also of degree less than or equal to 4, right? And why is that? Why can we do it of degree less than or equal to 4? Also, if I take kx mod x minus 1 cube, x minus 2 squared, every element is represented by a polynomial of degree less than or equal to 4, because this denominator has degree 5. And as I just said, if you have a denominator of degree k, then everything can be represented by a polynomial of degree at most k minus 1 using the Euclidean algorithm. So I have not completed this problem, right? But I've given you enough hints for you to be able to solve. So I want you to be able to actually do this by calculation. I want you to find a polynomial f of x of degree at most 4, which satisfies all these 5 conditions, these 3 conditions and these 2 conditions. So please work on it, and we will see in the next class. So there are some questions, I think. So let me just check. No, they are not questions actually, only comments. Okay. Are there any questions?
So what about the uniqueness of this?
Sorry, what uniqueness of what?
F.
Yes. Okay. So it's so coming to the uniqueness, right? So uniqueness in the Chineseeliminator. So it is unique for the fall. What is the exact uniqueness statement? So we know that Rmod I1 intersect Ik is isomorphic to Rmod I1 cross Rmod I2 cross Rmod Ik. Isomorphic, remember, it's not just surjective. This is an actual isomorphism. What this means is, so given B1 bar up to Bk bar in this ring, there exists a unique x bar in Rmod I1 intersect Ik such that x bar equals B1 bar, B2 bar up to Bk bar. That means it is unique up to the ideal I1 intersect I2 intersect Ik. In other words, if we have 2 solutions, x bar and y bar, then x minus y belongs to I1 intersect I2 intersect I2. So it's not fully unique, but unique up to. So for example, we know that Zmod, let's say 15z is isomorphic to Zmod 3z cross Zmod 5z, right? So for example, I could take the element, let me take just 1 bar 0. Right? So let me take the element 2 bar 0. So suppose I take the element 2 bar 0 bar. I want an element here which goes to 2 bar 0 bar. That means I want an element which is congruent to 2 mod 3 and which is congruent to 0 mod 5. So 5 itself works. So 5 goes to 5 bar 5 bar. But 5 bar is the same as 2 bar in Zmod 3Z, and 5 bar is the same as 0 bar in Zmod 5Z. So 5 goes here. So 5 is the solution. But 5 is not the only solution. I could take 20. 20 goes to 20 bar, 20 bar. But 20 bar and 2 bar are the same mod 3Z, because 20 minus 2 is 18, is divisible by 3, and 20 minus 0 is divisible by 5. So 20 bar is 0 bar and Z mod 5Z. So 5 and 20 are two different solutions. But you should not really think of it as different, because in Z mod 15Z, they are the same. In Z mod 15Z, 5 bar and 20 bar are the same. In fact, the only solution in Z mod 15Z is 5 bar. It's unique. The only solution in Z mod 15Z is 5 bar. So it is unique in this sense. It's unique up to the ideal, which is the intersection of all the I1, I2 up to Ik. Is that satisfactory?
Yes, sir. Yes.
Okay. Any other questions? Okay, so somebody asked me last time what book I was following. So it is the book that was, the chapter 1 was sent to you. It's the book by Atiyah MacDonald on commutative algebra. It's a wonderful book. I'm just doing parts of chapter 1. So far, I've not even covered the whole of chapter 1. I've just covered one topic in chapter 1. So the next 3 lectures, I'll try to cover some other topics still from chapter 1. And if there is time, I'll go to chapter 2, but I don't think there will be time. Chapter 1 itself is a wonderful chapter. It has lots of things, and one particularly good feature of this book is the large number of problems that it has. So in the handout that was sent to you, you will see that there are so many problems. Please do try the problems. Try to read the book on your own and try to do the problems. And I mean, trying to read a book means doing the problems is essential, right? So you have to do the problems if you want to understand what is going on. Okay. So if there are no other questions, hardest book also. Yes. Okay. As for comment, one comment says it's the hardest book. Well, in a sense, it is much harder than the books that you might be used to, because almost every line of it will need proof. If you read one line of it, you'll have to prove it. Then you read the next line, you'll have to prove it. It's true that it is hard that way. It's very terse, but it's extremely beautifully written, and you will learn a lot. Going through this book, you will learn lots. It's a small book, but going through that book carefully, you will learn a lot, much more than you will by reading some 300-page book, which just goes on discussing things without actually, doing much. It does a lot in a few pages. Okay, so we will stop here for today. Thank you.
So Gopalakrishnan also is very good.
Sorry?
Gopalakrishnan. Commutative algebra by Gopalakrishnan is also, I think.
Yes. Yeah, that is also there. But it does not compare to Atiyah MacDonald.
Yeah, that's